Hey everyone, thanks for joining. This is Ankit there. So today we wanted to talk about the real-time analytics scenario at Uber, how we use the power of Presto and Pinot to support like real mission critical use cases here. So to quickly go over the agenda, like I'll start with like a basic high level overview of like how things are laid out, followed by some use cases, and then Dharak will take over for some architecture innovations, and Christina will like also add there and like close up with Q&A. To give like a high level overview of like how things are. So I think as some of you might already know, Uber has a big Presto cluster, which is used for batch analytics primarily. The Presto deployment for the real-time analytics use case is a bit different in the sense that uh, it is not like it's a totally different service, and it is also like a different way of deploying Presto to the point that we call it like a different service altogether called Neutrino. And the difference between the Presto deployment and the Neutrino deployment is that we have like a single JVM which contains both the coordinator and the worker. So essentially, you can think of it as any other microservice that you might have. So let's say we have like 10 instances of Neutrino. Each of them is a Presto coordinator plus worker. So in a sense, we have like 10 pairs of Presto coordinator worker for let's say 10 instances of Neutrino. So yeah, it's a totally different way of deploying Presto. In terms of like how the Uber deployment environment sees it, it's just like a microservice. Like it's nothing different than that. Like all the semantics are the same. We do have like graceful shutdown, graceful startup, all of those things. So it's basically just like any other microservice. Um, a big difference between the Presto deployments and this particular deployment is that we are aiming for like ultra low latency. Like we are looking at around 70 milliseconds or 100 milliseconds for the most part. And we also serve like at a very high QPS. So for example, I think it's very common for our deployments to like support, let's say 2000 to 5000 QPS per region. And yeah, the design is like in such a way that we want to like maximize Pushdown. We want to leverage the underlying storage engine as much as possible. At the same time, also like add the goodness of Presto on top of it, like provide like a Presto SQL interface for all our customers, so they don't have to like change or understand like a new language. At the same time, also give like more functionalities on top of the existing Pinot layer at the bottom, which we'll talk about in the innovation section. Dharak and Christina will take you through it. At a high level, this is how the architecture is like. So the core is obviously like Pinot. Like Pinot is where the data is stored. It's doing most of the work on the query side as well. Then there are two questions, like how do you query this data and how do you get the data in there? So on the query layer, which is at the top, you'll see like there's like a Neutrino, which looks like a proxy, but it's not exactly a proxy because it's like adding like a bunch of features there. But essentially all the traffic that goes to Pinot goes via Neutrino. And this traffic is coming from like multiple sources. So we also like provide like an ad hoc UI where people can like run queries and do some ad hoc analysis. We have like bunch of services, microservices, which are hitting these APIs. And again, like they are looking at very low latency, like 10 milliseconds, 100 milliseconds, 50 milliseconds, and so on and so forth. So that's the query layer. On the data ingestion side, we have a framework called uwork. So basically that allows you to create data pipelines in a drag and drop fashion. So let's say you have a Kafka topic and you want that to flow into Pinot, then you basically like create nodes and create an edge to indicate that, okay, data from here is going there. Similarly, if let's say you have a data in the batch data world, like let's say you have a Hive table and you want to get that data into Pinot, then you like create like a Hive and Spark job. So yeah, the uwork framework abstracts everything, and internally like we create like different pipelines for the different scenarios. So the first scenario is the Kafka AthenaX ones, where we are looking at like real-time tables. Like these are tables which have like freshness around 5 minutes maybe. And for the batch data world, we are looking at freshness around 2 days and so on. So as you might know, I think Pinot can query both real-time and offline table at the same time. So this is how the data ingestion layer is carried out. Yeah, in terms of like the use cases, There are a bunch of use cases. Actually, we'll go through 3 right now, and we are still working on like more use cases this year. But to start with, I think the best one to start with would be orders near you. So this is right now in the app as well, based on like whether it's rolled out to you or not. So all the features, as you might know, like are rolled out based on segments. So yeah, the orders near you feature is basically it gives you like a new way of discovering new restaurants. For example, like if let's say you are much tired up to ordering from the 3, 4 restaurants that you usually order to, you can use this like as a good way to understand okay, how people around me are ordering. And it's in the carousel, and it requires like actually a functionality which was not there in Pinot before, and this was something that was contributed by the Uber team. So and the functionality is geospatial indexing and the geospatial types. So this was added last year by Uber, and this was a key business use case that came to us, and we also like contributed back to open source. So this was one feature that we added, and we are serving at a very high QPS again, like 800 to, I think sometimes it spikes up to 3000 as well. And yeah, the query latency is like 50 millisecond expectation. Next up, we have like the restaurant manager. So this is again like a very, very crucial part of the Uber Eats platform. So we have like around hundreds of thousands of merchants all over the world using this dashboard. And essentially every restaurant manager, if we can call them that, use this to figure out like how well their orders are doing, which they can also like see the ratings in real time. They can also see like which food items are the most popular ones right now. And they can also see like surge in demand over time, and what's the best time. Let's say you want to figure out like what's the best time to have more people at the restaurant, because this is the peak time where you serve more customers. So things like that, like, and a bunch of like other analytics, like a bunch of them are provided by the Neutrino Pinot combination. Again, the data freshness requirements here are 5 seconds, and we also like hold data for longer here. So the offline tables do help us out here. And yeah, the query latency again, like here, like we usually look for around 1 to 2 seconds because the query shapes are a bit expensive. So yeah, and next up we have Terra. So Terra is like an internal tool used by city house folks to figure out like how well cities are doing in terms of demand and supply. If let's say there is any imbalances, you can quickly see on the tool here. And this is again like a tier 0 functionality. If let's say it goes down for 5 minutes, it's a L5 highest outage. So it's very important to figure out, for example, like things like for a given city, what should be the radius of like how many restaurants should be available based on demand and supply and other factors. So all of these are provided by the real-time analytics platform. And yeah, this is like a very important tool, as you can imagine. Again, the query latency around milliseconds, data freshness. In this particular case, I think it's very easy to see the data freshness has to be as early as possible, because you want to detect issues as early as possible. So yeah, I think these are the use cases. Now I'll hand over to Dharak to go over the innovations.
Thank you, Ankit. So now we'll go a bit into the architecture of the real-time system that powers the use cases that Ankit mentioned. Ankit, I think we skipped a slide. Yeah. So this is how the architecture looks like. At the very top, we have the client, which are the use cases that Ankit mentioned. They can query the RTA system directly via HTTP on Muttley, which is like the load balancer we have at Uber, or they can use the Presto client and talk to the RTA as if they are talking to a Presto cluster. So within the RTA, we have the query service, which is essentially a type of Presto deployment, which we call Neutrino, which does the query planning, query translation, and also like executing the query to Pinot and doing some post processing if necessary. So Neutrino for metadata goes to our own meta store, and for the data in the case of Pinot, it talks directly to the Pinot broker. We also have this schema lesson Cassandra connector operational in Neutrino at Uber. How we'll go into the key changes that we have done in Presto, which kind of makes it Neutrino. So the first one here is the aggressive and complete push down. So here the agenda is to maximally leverage the underlying engine. What we do here is like given a Presto query, we try to form a Pinot query which has the maximum operations out of the Presto query, and then execute that Pinot query and do some post processing on the data if possible. So in this case, even we push down like operations like aggregations, group by, and joins. We leverage the Facebook's connector plan optimizer framework for this. We will see this in more detail in the next slides. The second innovation is like reducing the latency overhead. Since Presto traditionally is used for interactive analytics, the Presto overhead tends to be around 800 millisecond to 1 second, which is okay for interactive analytics, but for real-time analytics, it becomes a bottleneck. So we did a few architectural changes to Presto and how we deploy Presto to get it down to 70-ish milliseconds. So for this, we changed the Neutrino deployment to act as a synchronous microservice rather than a coordinator plus workers cluster, which also made Neutrino stateless and like horizontally scalable. And the next two changes are related to push down of like specific operations like joins and subqueries. So now for the aggressive push down. So as I mentioned, we use the Facebook's connector optimization framework here. So what this framework offers is it offers a plan subtree to the connector, and now connector can take part in optimization and can return a new plant tree to the Presto planner. So in this case, what we do is we find out the max plant subtree of the Presto query, out of which we can form a Pinot query which can be executed by Pinot. In the ideal world, we should be able to push down the entire tree, but since the features in Presto and Pinot are not the same, we have to do some processing to find the part of the subtree that we can push down to Pinot. So here you can see we take this subtree rooted at the aggregation node and convert it into a simple scan node, which contains the Pinot query that will fire to the Pinot broker. To see this in action, like so for a query like this, which has an aggregation and some filters, if you see on the left, the plan has like aggregation node, a final and a partial, and a scan filter per project node. But after applying the connector optimization, the plan becomes a simple scan node, and the scan node has the information of that of what PQL it needs to execute on Pinot. So the second overhead, so second innovation, as I mentioned, was reducing the overhead. So the change we made in the deployment structure was that rather than having one coordinator and workers, now we have coordinator plus worker combination running in the host, and we have multiple such hosts running in our Neutrino cluster. So now what happens is that each host can accept the query, and each host can like fully execute the query end to end. So this makes Neutrino horizontally scalable and also stateless. So once that is fixed, we found that the overhead here mainly came from the coordinator worker communication of task assignment and split assignment. So the problem lied in the frequency and also the communication method. So we worked on reducing the frequency by doing things like we changed the plan to have a single state, since we do very trivial operation in Presto itself. And for the communication part, what we did was we changed these communication HTTP calls into a local JVM RPC call, since now we have coordinator and worker in the same host. So this and plus a few more optimizations around split assignments and removing the resource group constraint helped us achieve a little latency overhead of 70 millisecond. So now the third thing is like push down of join. Why this is a bit different is because in Pinot we can't do join. We do a decoration / lookup from a dim table via a UDF. So to support this, we implemented join push down in Presto, where we take the subtree rooted at the join node and push the dim table scan node into the scan node of filter node. And now this scan node contains the PQL, which has the aggregation and also the hookup function. So, so to show you an example, like if you see on the left, the Presto QL has one fact table sales and joins with dim table products and stores, and we are simply just getting the columns name, price, and store name from the dim tables. So now this Presto query gets pushed down to Pinot as this quick query on the fact table only, and has the lookup function to get the name, price, and store name out of the dim table. So now I'll hand it over to Christina to talk about this subquery for Pushdown.
Yeah, thanks, Dharak. Next slide. Oh, yeah. So first, let's look at the Presto query on the left side. As we will know, it's common to use filter on an ID field with a list of venues, just as the query did. We are selecting username and clicks from the table. Well, we also check if the username exists in a given name list. So here we push down the query and translate it to the Pinot query on the right side. So these two queries look pretty much the same because we are translating the in operator from Presto to the in operator in Pinot. The query works fine if we only have, previous slides, please. Yeah, so the query works fine if we only have 20, 30, or less than 100 names. But think, what if we have thousands or tens of thousands names here? The issue is the query performance will be degraded. So there are two reasons. First, in Neutrino, the planning time will be high. As we have noticed, query with around 2,000 IDs can have around 2 to 4 seconds latency in Neutrino. And also in Pinot side, it also takes time to transmit the large query, deserialize the values, and construct the predicate evaluator. So all of this will hurt the performance of the query. So we have come with a solution. Next slide, please. Yeah, so please take a look at the query on the left side, which serves the same purpose. So instead of passing the names to the query one by one, we use a subquery to generate the name list as the output. So here we push down the in subquery syntax and we translate the query to the Pinot query on the right side using Pinot ID set function. The Pinot ID set function is rolled out last September, which is originally designed to solve this kind of filtering issues. So here we can optimize filtering on a large number of venues, like thousands or more, reduce the size of the query for better performance. Next slide, please. Yeah, so here comes the fourth innovation at Uber. We push down subquery to Presto-Pinot connector. We use Presto in subquery syntax, and we write the subquery to use Pinot ID set function. So this is the query we just talked about. And on the right side, this is the logic planning tree. As we can see, there are two important nodes here. The first is the semi-join node, which holds information about the in subquery syntax. And on top of the semi-join node, we have the filter node. Well, the filter node indicates whether the username exists or not exist in the subquery. So here, to add a support, we add a visit function for the semi-join node. So in the semi-join node, we detect this kind of query patterns, and we translate it to use our Pinot ID set function. And here, in this way, we are able to flatten the original logic planning tree to the final one with only two nodes. One is the output nodes and one is the table scan nodes. However, there are still some limitations we have about what kind of subquery we support. There is no aggregation, no group by, and order by where limit is allowed in the subquery. And this kind of limitation comes from the Pinot ID set function. So they don't allow this kind of expression exists, so we don't allow it in Neutrino as well. And also because the Pinot ID set function is an in-memory data structure, so when you have a very long list of names coming from the subquery, you may have high disk usage. Next slide, please. So having talked about the use cases, the architecture, and also the 4 innovations at Uber, we have learned 2 things. The first, in practice, measuring latency overhead is really hard. So usually we will add a logging here, but we are looking forward for an easier way to do it. Second is we should focus more on the business use cases and impact. Understanding this help us to prioritize features. What kind of features we want to add to the Presto-Pinot connector. And about the future directions, because for our platform, most of the users will have very fixed query patterns. So we are trying to find a way to add a plan catching to reduce planning time. Because with this, we will help all the users to help reduce their query latency. And second, we will continue working with the customers to understand their use cases and close the gap between Neutrino and Pinot feature sets. And also, we are going to leverage Neutrino for alerting and monitoring mission critical metrics at Uber. And also integrate Neutrino with visualization tools, which are also requested by our customers many times. Yeah, so here comes the QA session.
Yeah, so I think we have two good questions so far. One question is, how does push down of operations like join is performed, since the like connector optimization does not contain join operator? Is it available in the latest PrestoDB? If so, please point me to the link. So I'm not aware of the status of the latest PrestoDB, but we have implemented this internally at Uber. We have moved the join node to SPI and also added the connector optimization support. I believe it's in the process of being open sourced. I think Ankit and Christina can share more on that.
Yeah, I think we have this and a few other features that we have internally, but we haven't open source yet. I think most likely this year we'll pick up some of this backlog and get this merged back to open source, if that helps. Yeah.
Yeah, the second question is that an entire quick query can be pushed down like Spark. If not there yet in Presto, what needs to be done to push down entire query? So if I'm not wrong, to push down the entire quick query, we would need support for the connector optimization framework to handle all kind of plant nodes, and then the connector optimization can work to push down each of these plant nodes.
I think there is another question on more information about the on-prem deployment. So yeah, for Neutrino, like we have, I think it's like just every other microservice. Like we have each JVM, each Neutrino instance is basically a JVM and a single JVM, which has both the coordinator and the worker. And I think, as Dharak mentioned, the coordinator and worker interact with each other using RPC calls, like JVM RPC calls, and not HTTP calls. So essentially, everything works within the process. And we have different Presto clusters. We have different tenants based on like different use cases, and all the users only use the Neutrino interface, which is like the Presto interface. So, for example, like some of the use cases, they use the Presto driver to actually connect to Neutrino and run their real-time analytics queries. So, yeah. Is there any plan on caching query plans from coordinator to Pinot? Yeah, I think that's one of the plans that we have. We are planning to like look into this, but yeah, I think let's see like how well it goes. This itch. But I think this can really help in like really making Neutrino very lightweight. For example, a lot of most of the queries are actually have the same query fingerprint. So there's like a lot of room for not having to do the plan generation again and again. So yeah, I think there's a lot of room for that there, and we're most likely going to look at it this year. So yeah, I think like Christina, if you want, you can also take any questions. But yeah, the next question is the Pinot ingestion question. If historical data is changed one day later, rival data, do you need to rerun Spark to ingestion updated yesterday's data to Pinot? So I think for the latest data, we do support like upsert in Pinot, and I think we do have upsert servers. And yeah, for I think historical data, I'm not sure like what we do there. But yeah, I think for the real time ones, we do use the upsert feature in Pinot to do those updates.
Yeah, I think it's right for the historical data. If it's changed, we need to like recreate the segment for that particular date. So basically run the Spark job again for that day.
Yeah, I think the next question is any way or plan to support pushdown UDFs from Presto to Pinot? I'm not sure like what does pushdown UDFs mean? Like, do you mean like what exactly does that mean? Dharak, Christina, are you aware?
Not sure. I think it might be might be about like the UDFs which are specific to Pinot and are not present in Presto.
Yeah, I think the strategy we follow is that a lot of the transition we have like some UDFs which we do transfer to the Pinot corresponding Pinot UDFs. I think if that helps answer the question. Yeah, I think Nexus does it integrate well with open source Druid, or what would be the difference? I'm not sure we have tried that. Dharak, do you know?
Not really. I think we do have a Druid connector which operates in a similar fashion, but I'm not really sure.
Yeah, there is a Druid connector for Presto as well, which also has predicate pushdowns. That's part of it. It is also kind of being actively worked on in parallel, but it's different. I mean, in some ways, it's different. So if it would be a completely different connector.
Sure. Yeah, so I think the next question is Pinot accessed directly for any use cases? If not, then can you share why not? So I think we do have another service, which is like mostly like a legacy service, which serves some traffic. I think it's around 5% of the total traffic, which is like we call it Pinot REST proxy. It proxies some of the traffic, and it serves like a PQL interface for the queries. And we want to like standardize all the queries to use Neutrino because we get like a common interface for all the queries. That is one. And I think the biggest one would be that Presto integrates very well with a lot of things. So you don't have to like implement specific connectors. For example, like Data Studio connector, like you wouldn't have to do a lot there. You can keep reusing the Presto connector that is already there. Similarly, for like we have an internal system we call like Query Runner, which basically like is a way for people to like run their queries for multiple engines. So it has a Presto connector already. So we actually piggybacked on that. We didn't implement like a new connector for Pinot. So and of course like the previous innovations that Dharak talked about. So Dharak and Christina talked about. So yeah. I think next question is an interesting one. Running the Presto coordinator on multiple nodes, can I assume that we are running the same query in multiple coordinator nodes? Is that not an overhead? So I think we don't run a query on multiple nodes. So every query runs on a single Neutrino instance. And the way it runs is that, let's say a query comes to the Neutrino instance, it will be forwarded to the Pinot cluster, which will be the appropriate broker for that query. And the results will come in. And if there's any post-processing that needs to be done, that will be done in Presto. So that will be done in that Neutrino instance. So it's like a single Neutrino instance runs the entire query end-to-end in a way, except the Pinot processing, obviously. But yeah, so we are not running a single query across multiple Neutrino instances. It's only boxed to like one instance. Since we're running out of time, I'll quickly go over. Is there a future direction of embedding security as code into the application to make your databases completely dark from the internet, eliminate the use of VPNs, jump servers, and bastion hosts? I think the key thing here is that within at least our deployment, we are only looking at traffic which is originating from within the data center. And we have a unified gateway for all external traffic coming in. If that helps, and that takes care of basically all terminating all the security and everything. So internally, like we do have like some security, but we don't have to focus too much on it because usually we are gated at the gateway layer itself. And yeah, finally going through Presto, what do you mean by optimization support for? Yeah, I think Dharak, do you want to take this?
Yeah. So I think yeah, that's what I essentially mean. But I think the main quick question for doing a full query push down would be like the parity between the two engines. So like so for example in Presto and Pinot, so like there is no one-to-one parity. Like so to push down the entire Presto query to Pinot is not possible because like the feature sets are different. But like let's say if you find an engine with which is like the exact one-to-one feature set connection, then I think it's like matter of implementation, as you said.